everyone. Welcome to Learning at 11th Hour. We all know that the NAND and the NOR gates are the universal gates. In this video, we're going to see why. So we can implement practically any boolean equation or any boolean function using just the NAND and the NOR gates. Let's see how this is done. But before we dwell into this, there's a small note that needs to be addressed. So we all know that the NAND gate can be represented as the AND gate with an inverter bubble. So if this is my NAND gate, I can also call it as the AND invert. Now, if I apply the De Morgan's law, it says that this is going to be this, right? So x dot y, the whole bar is x bar plus y bar, wherein this plus represents the OR logical operator. So now let's try to implement this function. So we need an OR gate over here, and we have, say, the same inputs x and y that are available to us. So before we allow the signal to enter into the logic gate, we introduce a inverter into it. So if this is x, what goes into the gate is going to be x bar. Similarly, if this is y, what goes into the gate will be y bar. So ultimately, the output for this is going to be x bar ORed with y bar. So then can we say that if this is x dot y the whole bar and this is x bar plus y bar, practically this means the same, right? So this is nothing but an invert OR. So and invert is the same as the invert OR. Let's look at another situation. Suppose I have the NOR gate. So here we have the OR gate with an inverter at the output. This becomes our NOR gate. So that is x plus y the whole bar. Again, when we apply De Morgan's theorem to it, we know that this is equal to x bar dot y bar. So now if we try to implement this, we need an AND gate, and the input should be inverted before it is sent into the gate, so that we have x coming in but going into the gate as x bar, y coming in and going into the gate as y bar. So what ultimately comes out is x bar dot y bar. So can we say that the OR invert is equivalent to invert AND? So this is scenario 2. Lastly, let's look at the concept of inverter. So an inverter in terms of the NAND and the NOR. So when we have a NAND gate and we have both the inputs the same, what happens? So let's look at the truth table of the NAND gate. If x and y are the two inputs, 0 0 0 1 1 0 and 1 1, and this is the output of the NAND gate. So it's going to be 1 1 1 and 0. Now let's just focus on the inputs where both the inputs are the same. So that's 0 0 and 1 1. So when both the inputs are the same, right, I can just consider it as a single signal X, right? So when both inputs are the same and when it is 0, the output becomes 1. When both inputs are 1, the output is 0. So that means if I send the same signal through both the inputs of a NAND gate, I'll get the inverted version of it. So this is practically the um, AND with invert, where both the inputs are the same. This is the inverter, the NOT gate. In terms of NOR also, we can have the NOR gate with both the inputs the same, and then we would get the inverted version of that input at the output. So we can verify this also with the truth table. if we have two inputs and this is the output of the NOR gate. So here the output of the NOR gate is going to be 1, 0, 0, 0. Now let's just focus on the situation where both the inputs are the same. So 0, 0 and 1, 1. So when the input is 0, the output is 1. When the inputs are 1, the output is 0. So that means the output gets inverted when the same input is fed into both the terminals of the NOR gate. Now, having said this, we can now use these notes as uh, the basis for implementation of any Boolean function using the NAND and the NOR gates. Let's take up an example and see how this is done. Say we need to implement the function f is equal to ab plus cd as the example. So normally how do we do that? So we need four inputs. We have A and B. We'll combine it with the AND gate. So what we get here is AB, and we have C and D. We can combine this again with another AND gate in this manner. Now these two outputs can be combined using the OR gate. So F is the output of this implementation. Now, if I want to convert this into a NAND implementation, then how can I do this? So to do that, what I need to do is I need to understand that this AND gate can be converted into a NAND gate by introducing an inverter over here at the output of the AND gate. But in that case, what would happen is this output, which was A dot B, would now become A dot B bar, which is something we don't want. We don't want the expression to change. So to nullify that effect, we can introduce another bubble at the other end of this wire. So effectively, what enters this OR gate is A dot B bar, the whole bar. A dot B bar coming out from the AND gate, in fact this NAND gate, and entering into the OR gate as A dot B bar, the whole bar. The same thing can be done for the second AND gate. So this becomes my NAND gate. So I can introduce another bubble over here to nullify that effect such that what enters into this is C dot D bar, the whole bar. So the bar and bar cancel out and what enters effectively is C dot D. Now, if we look at this particular implementation over here, so this is invert OR. This is the invert OR configuration. The invert OR is nothing but another representation of the NAND gate. So therefore, I can rewrite or redraw this circuit as three NAND gates because this is going to be AB, this is going to be CD, and the two can be combined using the invert OR, which is also a NAND gate. So now this is the NAND implementation of my function f. Let's look at another example. Say we need to implement the function f of x, y, z is summation of 0, comma 6. So what does this mean? So this means that I can represent this using the k map and I can find the expression, or I can simply write out the expression using the number of the minterm over here. So while I represent it in the k map, this is going to be x, y, z, 0, 1, and this is 0, 1, 2, 3, 4, 5, 6. This is 6. So these are the two minterms. Even otherwise, I could write the minterm directly also as x dash, y dash, z dash plus x, y, z dash. So this is f. Now I need to implement this using the NAND gates. So having said that, when I say NAND, it means that it's going to involve product terms, and therefore if I have the expression in the SOP form, it will be easy for me to convert it into the NAND implementation. So right now I have it in the SOP form, so no worries. Now let me directly implement it. I have x dash, say is the input, y dash, and z dash. I'm considering that this is the inverted versions of the inputs that are available. So all three put together, this is the first term. Now I can have the second term over here as x, y, and z dash. So I've put bubbles over here so that the x dash and the y dash get inverted. Both of them put together with the OR gate. So here I have x dash, y dash, z dash. Here I have x, y, z dash. And here I have combined both using the OR gate. Now, since I have the NAND over here, uh, I can obtain the AND, from the AND I can obtain the NAND by introducing a bubble at its output. But if I do that, I have to compensate it by introducing the bubble at the other end of this wire. The same thing is applicable over here also. Now, these two bubbles represent inverters or NOT gates. So if I want to incorporate that, I can again use NAND gates for it. So this is the first NAND gate, this is the second NAND gate, and over here, this is also a NAND gate, as can be seen from the invert OR configuration or invert configuration. This is first stage is inversion, second stage is OR, and that represents a NAND gate. So I can redraw this as NAND gate with the three inputs x dash, y dash, z dash, and I can have another one where this is x, this is y, this is z dash coming from here, all three put together into another NAND gate. Both of these combined with another NAND gate. So this is going to be x dash, y dash as connected from the other inputs over here, and therefore here I would get xy. So effectively we have 1, 2, 3, 4, 5. We have 5 NAND gates used to implement this particular function. Now can the same function be represented using the NOR gate? So let's look at the NOR implementation of this. So NOR implementation would mean that I would require the expression to be in the POS form. So if that is the case, so this is my function, and I have the K-map as this. These are the two minterms, x, y, z, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. So if I want to obtain the POS, I need to group the zeros. It'll be easier for me in that case. So let me complete this K-map and let's form some groups. So this is a quad, this is a pair, and this is a pair. So we have now grouped zeros to obtain the POS. So let's write the expression for this pair in terms of POS. So POS is going to be just the inverted version of how we obtain the expression for SOP. So if there is a 1, then in the expression we should use it as the inverted part. So if this is x over here, we should call it as x dash for this pair. And looking at the columns, 0, 0. Y is 0 in both of these columns. So we should keep it as y, and the two terms have to be combined with an OR gate. So this is the first term. Let's look at this one. So analyzing the row first, here x is common for both the zeros and the value of x is 0 over here. So we'll keep it as x instead of x dash because we're looking at POS, and we have to combine it with the column. So in columns, we see z is changing from 1 to 0, whereas y is 1 in both cases. Since it's 1, we have to return it as y dash. So that is the expression for this pair. And for this quad, the expression is going to be, we see that z is 1 for this quad. That is the only common term. So we keep it as z bar. And how do we write the expression? We write it as x plus y bar dot x bar plus y dot z bar. So now this is the POS version of my function. So if I simply implement it, I will get x and this is y. So I need y bar. So I have combined it with an OR gate. This is the first term. Next, I require x bar and y combined with the OR gate. That's the second term. And the third term is z bar. Now all the three have been combined with the AND gate. So here we have x plus y bar, x bar plus y on this line, and this is z bar. Now if I want to implement it in the NOR form, so I can convert the OR as NOR by introducing a bubble at its output. So to compensate this, I have to introduce a bubble at the end of this wire. The same thing should be done over here. And here, since this itself is a bubble, we can remove this and put it here. So what comes in right now is not going to be Z. It's coming in as Z, but entering the gate as Z bar. So now here I have invert AND. So let's go up and check what invert AND is. So here if you see, invert AND is nothing but NOR. So having said that, we can now redraw this circuit. So how do we redraw it? We can obtain it as the first one, the second one, and combined with the third input using a third NOR gate over here. The input to this is X. Now for Y, I need Y bar at the input of this. So I can use another NOR gate over here like that. This has a Y over here, and for X bar, I can again have another NOR gate like this, because after all the NOT gate can be represented using the NOR by making both the inputs of the NOR gate the same. This one is Z. So effectively we get the same terms that we've got over here. So this is the implementation of function F. So this is NOR implementation, and the previous one that we saw was the NAND implementation. So we can implement any function using both NOR or NAND, purely NOR or NAND. For obtaining the NAND, we need the expression in the SOP form, and for NOR, we need it in the POS form. So that's all with today's video. I hope the NAND and NOR implementation of Boolean expression is clear to you all. If you have any queries, please do not hesitate to post them in the comment. Please do subscribe to this channel, and thanks for watching.